There are very few problems that you can solve exactly in quantum mechanics. Because of that, we have to rely on methods of solution that give us approximate answers. And so one of the nice methods to use is time-independent perturbation theory, and that's the topic for today's lecture. Now, there are other methods, some probably none of which we'll cover in this course. So, for example, there's the WKB method, there's the variational method, there's time-dependent perturbation theory, all of which you probably will pursue if you take quantum mechanics at the graduate level. But a very nice bunch of examples can be solved using time-independent perturbation theory. So let's start with that. Let's say we were able to solve the Schrödinger equation for some run-of-the-mill potential, maybe the particle in the box, for example. Let's call the Hamiltonian H0. So this is the unperturbed Hamiltonian, and we have these unperturbed eigenfunctions and eigenvalues, and so, of course, that's the solution for a standard problem. Now let's say, though, suppose that we wanted to perturb it. So, as we were at the beginning, psi sub n0 is just the complete set of orthonormal eigenfunctions, such that psi n, psi m would be Kronecker delta n and m. And we were able to obtain the eigenvalues, E sub n, and so on and so forth. But now let's say we want to make the problem more complicated. Suppose we want to perturb in a time-independent manner the potential. Well, now we have to find new eigenfunctions and new eigenvalues. And so maybe for my new system, I would have something like h psi sub n equals E sub n psi sub n. If that's the case, we probably won't be able to do this exactly. And so we're going to use time-independent perturbation theory to get an approximate solution to the problem. The way you do that is you start with the solution to the unperturbed problem and then build on it. So first thing we're going to do is let's write our Hamiltonian using two terms. My unperturbed Hamiltonian plus lambda times h1, where h1 represents some perturbation of the Hamiltonian. Lambda is assumed to be a small number, but ultimately we're going to take the limit as lambda approaches 1. That will be later on. So we're going to write psi sub n and E sub n as a power series in lambda. So I'm going to write psi sub n as psi n 0 plus lambda psi n1 plus lambda squared psi n2, and on and on and on. I'm going to write my energy eigenvalues E sub n as E sub n 0 plus lambda E sub n1 plus lambda squared E sub n2 plus on and on and on. So what we call E sub n1 the first order correction to the nth eigenvalue. Psi sub n1 is the first order correction to the nth eigenfunction. Now, what we'll do then is substitute psi sub n and E sub n, the power series, into the equation h psi equals E psi. And we'll get h0 plus lambda h1 and h1 times psi sub n0 plus lambda psi n1 plus lambda squared psi 2 plus on and on is equal to En0 plus lambda En1 plus lambda squared En2 times psi N0 plus psi N1 plus times lambda plus lambda squared psi N2, etc. So it makes a real mess. What we want to do then is collect the like powers of lambda. And if we do that, we'll get H0 psi N0 plus lambda H0 psi N1 plus H1 psi N0 plus lambda squared H0 psi N2 plus H1 psi N1 plus ... equals E sub n psi sub n0 plus lambda E n0 psi n1 plus E n1 psi n0 plus lambda squared, and so on. Let's start easy. Let's just do it to first order. So to first order, I'm going to write psi h psi n1 plus h1 psi n0 equals E n0 psi n1 plus E n1 psi n0. So that's to first order. To second order, it's a little bit more complicated. H0 psi n2 plus h1 psi n1 equals E n0 psi n2 plus E n1 psi n1 plus E n2 psi n0. So now that all the orders are straight, we're just going to let lambda equal 1, and we're good to go. Let's look at first order theory. Let's start with that. That's going to be a little bit simpler. Let's take this equation and multiply every term by psi n0 star. In other words, we're doing an inner product. So that will give us a third equation. Psi n0, h0, psi n1, plus psi n0, h1, psi n0, equals En0 psi n0 psi n1 plus En1 psi n0 psi n1. We're going to assume H0 is Hermitian. So therefore, psi n0, H0 psi n1 plus is equal to H0 psi 0, 0 psi n1, which is equal to En0 psi n0, which is equal to En0 psi n0 psi 1. So notice, this is equal to the first term on the right-hand side of equation 3. So this tells me then En1 is equal to psi n0 h1 psi n0. And this is the fundamental result of first order perturbation theory, which says that to first order, the correction to the energy eigenvalue is just the expectation value of the perturbation in the unperturbed state. So H1 is the perturbation to the Hamiltonian, but psi n0 are the wave functions for the unperturbed state. Really? Let's see how that works. Let's apply it to the infinite square well. So we know that the eigenfunction for the infinite square, or the unperturbed eigenfunction, particle in a box or whatever, sine n pi x over a. Let's say we raise the floors of the well by some constant v naught. So in this case, my perturbation, h1, is equal to v naught, raising the floor of the infinite well. That means my energy eigenvalue, En1, should be my initial wave function with my perturbation in the middle, like so, which I can write as v naught's a constant. That's just psi n, which is, this of course is just 1, they're orthonormal, so that just gives me v naught. So what that says is the energy eigenvalue is just going to be equal to the initial energy eigenvalue plus some value v naught. Well, of course, that's what we would expect. It's an exact answer, and it means that if I apply a constant perturbation, all the higher order corrections above first order should vanish. Okay, well that was easy. Let's make it more interesting. Now suppose the perturbation only extends halfway across the well. How does that change things? Well, in that case, I'm going to write my new energy eigenvalue as 2v naught over a, integral from 0 to a over 2, sine squared n pi x over a dx. So if I integrate that, I'm going to get that my energy is actually equal to v naught over 2. So this result implies that the energy level is lifted up by v naught over 2. That's not exactly correct, but after all, it's only the first order. What about the correction to the eigenfunction? Well, if that's the case, let's write it this way: h0 minus En0 applied to psi n1 should equal minus h1 minus En1 applied to psi n0. Well, the right-hand side's a known function. So we have an inhomogeneous differential equation for psi n prime. So the unperturbed functions constitute a complete set. These guys, of course, we can write as a complete set. And we can write then psi n1, or any other function, as a sum m not equal to n, c sub m of n, psi sub m of 0. We don't need to include m equal to n in the sum, because psi sub n prime is satisfied by the dE, then so does anything like psi n plus some constant times psi n 0. So what this allows us to do is subtract off the psi n 0 term. All we need are the CMs. So sum m not equal to n, em 0 minus en 0, c sub m of n, psi sub m of 0 is equal to minus h1 minus p sub m psi n 0. P sub n psi n 0. Now, let's take the inner product of both sides with psi sub L of 0, another wave function. So we have m not equal to n, en 0 minus en 0, c sub m, and psi L of 0, psi m of 0 equals minus h1 minus en psi n 0. Sorry. Let's write that better. Is equal to, sorry, minus psi L0 h1 psi n 0 plus e sub n psi L0 psi n 0. Now, if L is equal to n, then the left-hand side is 0, and we get En1 is equal to psi 0 m h1 psi n 0. But if L is not equal to m, then we get, so L not equal to m, we get EL minus EN, C sub L, n is equal to minus psi L of 0, H1 psi n. Psi n of 0. Solve, and we get Cm, then n is equal to psi m0 h1 psi n0 divided by en0 minus em0. And then finally, we're going to get my new wave function, psi 1, written m unequal to n psi m0 h1 psi n0 e sub n minus e sub m0 all times psi m0. So this works as long as the denominator doesn't turn out to be 0. So, in other words, as long as the two states happen to don't share the same energy, it's non-degenerate. This completes, at least until, we'll do one example of this, but this is our treatment of first order perturbation theory. Any other non-degenerate first order perturbation theory, if we have a degenerate case where the two energies are equal to one another, we have to go further. Let's just do one example of this and see how this can apply to first order. Let's do an example with the hydrogen atom. Let's look at the effect of allowing the proton in the hydrogen atom to not have a point size. Let's give it an extension in space. We know that the nucleus, in this case for the hydrogen atom, just the proton, is much, much smaller than the size of the atom itself by an order of 10 to the fifth. But the radius, let's say, of the nucleus, the radius of the proton, is not 0. Let's see how it affects our even to first order. Our calculation for the first order energy for hydrogen, if we allow the nucleus to have some extent in space. So this is what we're going to do. Suppose we contain the proton in a spherical shell of radius r, where r, of course, is much, much, much less than the Bohr radius. So the size of the nucleus, or just the size of the proton, is much less than the size of the atom itself. Using first order perturbation theory, I want to calculate the changing binding energy for hydrogen because of the fact that the proton has some extent. So we'll do it this way. We'll assign a potential V of r equal minus e squared over r for 0 less than r less than capital R, which means you're inside the proton. And it's equal to minus e squared over little r for capital R less than r less than infinity. So those are my potential energies, right? Let's take the difference between V of r and e squared over r is the perturbation. So H1 is equal to e squared over little r minus e squared over big R for 0 less than little r, less than big R, and then 0 otherwise. Okay? So to first order, my first order energy correction, delta E 0 to capital R e squared over r minus e squared over capital R squared times r 10 squared dr gives me 4 over a naught cubed, 0 r e squared over r minus e squared over capital R squared e to the minus 2r over a naught dr. But since capital R is much, much less than A naught. We're going to say that e to the minus 2 R over A naught is approximately 1. That makes our delta E equal to 4 over A naught cubed. Integral 0 to R, E squared over R squared dr, minus integral 0 to R, E squared R squared dr over capital R. If I work out the integrals, which are fairly simple, I'm going to find that delta E is equal to 2E squared R squared over 3A naught cubed. So as delta E is as delta E is greater than 0, so my ground state increases because of my ground state energy increases because of the nature of the proton. The fact that we have some extent in space of the proton. And that's one example of how I can use first order perturbation theory in kind of a nice problem with the hydrogen